Hello again. Let's resume. We just completed Theorem 1.5, Gram-Schmidt orthogonalization process, and it proved not only that the orthogonal bases exist, but also we have a construction formula. We usually start from W1 only and then use this to get W2, and then W2 to get W3, and W1, W2, W3 to get W4, and so on and so forth. Let's see how about an example. Okay, here we go. Find an orthonormal basis of a subspace W generated by W1, W2, W3, where we have these. Okay, alright. So what we need to do is to use a Gram-Schmidt process, and in this Gram-Schmidt orthogonalization formula here, where is it? Yes, here. In this formula, let's copy and paste it over here. W1 through Wm are the orthogonal basis, mutually orthogonal set we already have. But here, W1, W2, W3 are the basis of the subspace W. So we'll have to use different character. Let's switch V and W. So we'll have to do it this way. V1 is equal to W1. Okay, alright, that's good. V2, we have to do it by W2 minus C1 V1, which is W2 minus, let's see, W2 dot product of V1 over V1 dot product of V1 and V1, like this. You see, what did I just do? I switched V and W because, I switched V and W by necessity. W3 minus C1 V1 minus C2 V2, but these C1 V1, C2 V2 can be misleading because they are different from this. So to avoid confusion, let's remove this, and then let's put C1 here. So I'll remove them later. So W3 V1 over V1 minus W3 V2 over V2 So I don't need this anymore. Okay, was I too fast? Please check with this. Okay, first one, I don't have to really do anything. I didn't get any head start, so there we go. And then W2 is C minus V2 will be W2 minus C1 V1, and V3 will be W3 minus C1 V1 minus C2 V2, and I may have to do one more if I had one more vector, but in any case, it's just application of this formula where V and W are switched off by necessity. The problem originally gave me W's. Okay, as for the computations are concerned, well, okay, here. And oh boy, I did the computation and then the dot product. You know what? And I can't follow this computation. I'm looking at it, but I can't follow. It's just this computation here. We are doing the dot products here, W2 dot V1. So we have to do this dot product in the numerator. And multiply the first. It looks like it. It looks like I am doing it right. And then we got something. Okay, all right. And it's okay to take this as my V2, but if I use my V2 like this, then next computation will be much more complicated because of these fractions. So I just multiply by 3 to make everything integer so that the next computation is a little bit more manageable. And I'm going to put that into the next one. And then how does that computation go? Well, again, I'll just show you the computation, but I don't know if I can follow it easily. Well, okay, we have a bunch of very, very elementary computation, but there's so many numbers I can't follow them. Looks like you'll have to take some time going through this computation and get your handheld calculator ready to make sure the computations are correct. And then in the end, get that. Okay. So we got the orthogonal basis, and once you get the orthogonal basis, you can get orthonormal basis simply by dividing each by the norm of each. So divide by square root of 3, divide by square root of 42, divide by square root of 105 to get orthonormal basis. Yeah. By the way, if I write the kind of problem in the exam, I'll probably stop at finding orthogonal basis. Orthonormal basis with these kind of computation, kind of pointless. As for how likely are you going to see this kind of computation problem in the exam, I'll say half and half. I mean, it's a good computational problem, yes. And then you have to prepare some formula sheet and do some exercises and then work on it. It may be time consuming, but you can handle it. The problem is there's so many problems like this that this kind of problems may show up somewhere in chapter 6, or there may be some other problems in chapter 7, or some other problems chapter 8. There are many computation problems, so I cannot really say whether it's really likely to see this kind of problem in the exam or not. For example, for the first exam, finding the inverse matrix using Gaussian elimination was pretty close to 100% because that was really important and there's no peer. But here, it's important, yes, but then again, there's so many problems that are in about the same level, so I cannot say anything definitively here. Anyway, we just went through a computational problem, and I hope I'll have another problem. Let's see, find an orthogonal basis of the space of homogeneous solutions of the following system. Okay, space of homogeneous solutions. If it is non-homogeneous, then it's not a subspace, but space of homogeneous systems of equations, then yes, it's a subspace. So how do you find it? Well, solve this system, and then you can find out vectors. And then let's see, we have 4 unknowns and 2 equations. So it'll down to 2 unknowns. So we're going to get 2-dimensional subspace here by finding out x and y. And then you get 2 bases from there. And then you can apply the Gram-Schmidt orthogonalization. Okay, let's see. First, let's find out the solutions. Oh, some elimination. Okay, all right. So elimination and then substitution. And then, okay, I got this. So z is solve z with respect to x and w, solve y with respect to x and w. So with x and w, we have all these. And then you can put appropriate values at x and w. X and w, excuse me. So plug in x equals to 1 and w equals to 0. Then okay, this is what we get. And put x is equal to 0 and w is equal to 1. We get this vector. I could have plugged in other values, but well, 1, 0, 0, 1, those are rather generic choice. So in any case, we got 2 vectors, this one and that one. And they're not collinear, so clearly they are not linearly independent. All right. And then what we want is, through the Gram-Schmidt process, we want to find out the orthogonal vector and take this one as my W1, and then this is V2, and you can use Gram-Schmidt process to find out W2. So okay, W1 is this. W2 is V2 minus CW1. And then, yeah, V dot W over W dot W. We have this, but I cannot follow this computation. In time, of course, I can do it, but quickly I can't do that. In any case, looks like I got this vector so that this is perpendicular to W1. And that's all I need, isn't it? I wanted orthogonal basis, so this and that. And if I want orthonormal basis, then of course I have to divide those by the norms and then normalize them. Then we have the unit vectors like these. Okay, all right. Tedious solution, Gram-Schmidt process, and the solution. Do I have time for this? Let V be a finite dimensional inner product space, same as a vector space with scalar product. Scalar product, inner product, they're the same thing. And let W be its subspace. Then dimension of W and the dimension of W perp add up to dimension of V. Okay. How do I do this? Can I use rank theorem here? No, I don't think this is a rank theorem. It's kernel and image. It doesn't look that simple. Looks like we'll have to do it hard way. Oh, what was I thinking? Excuse me. It wasn't that hard. It was much easier than that. So W can be written as a with basis W1 W R, oops, where these W's are mutually perpendicular. You can write like this. You can use Gram-Schmidt process, so you can always find out orthogonal bases, so W can be written like this. And then now we can use Gram-Schmidt orthogonalization. Then you can find out WR plus 1 all the way up to WN. So this is just Gram-Schmidt process. We can always get okay. From theorem 1.5, the orthogonalization theorem, we can find the orthogonal basis for W. From theorem 1.5 again, I can get the next basis, so that's going to be V. We must prove this. W perp is actually this. And that'll complete the problem. Now, if I prove this, that's going to complete the problem. How do I do that? Looks like I'll just leave that to your exercise. Pretty much everything is there. You see, W perp is a space where everything here is perpendicular to everything there and vice versa. And look at these bases. They're perpendicular. So yes, this is not going to be difficult to prove from this point on. I'll leave this as a hint and I'll stop there. If you're interested, you can open up this proof and then study it as well. But here in this video, I'll just stop here.